In this video, we will be discussing the defects in solids. More specifically, point defects. In the previous videos, we talked about crystal structures and what a crystal is. But the crystals, in reality, they are imperfect. They always possess some imperfections. And those imperfections are referred to as crystalline defects. The defects can be point defects, they can be linear defects, and they can also be planar defects. But in this video, we will focus in all of the types of point defects. The point defects control the mobility of atoms and therefore influence all processes that depend on diffusion. The first type of point defect that we're going to discuss is vacancy defect. It is a defect in which an atom is missing from one of the lattice sites. As we can see here on the diagram, this is the representation of a On the left, we have a representation of a perfect crystal, but on the right, we have a representation of a vacancy point defect where one atom is missing. The other type of point defect is the interstitial atom. It is an atom that is crowded into an interstitial site. An interstitial site is nothing more than a void space, which is a little void space. So you could add an atom right here, another atom right here, and these atoms are usually the same type of atom as the whole material. In metals, a self-interstitial introduces relatively large distortions in the surrounding lattice because the atom is substantially larger than the interstitial position. So when you have a small space and you add a big atom, all the other ones are going to be dislocated so that that new atom can be added to this small space. That's why it's called a defect. The next type of point defect is the substitutional defect in solid solutions. It is a type of solution where some of the solvent atoms are substituted by atoms of the solute, also called alloying element. So here we can see that we have a majority of silver atom, which is solvent atoms. In this case, the solvent atoms are the silver atoms, and the solute are the copper atoms. So here, a silver atom was replaced by a solute atom, a copper atom. And the same happens right here. That is a substitutional defect. In many cases, this type of defect is used to strengthen the material. Lately, we're gonna look at the formation of steel, and that's through adding impurities to the molecule. And this is one type of impurity. Now, there are some rules for an impurity atom to form a substitutional solid solution, and those are called the Hume-Rotary rules. And now we're going to go look into each one of them. The first rule is that the atomic size factor must be less than 15%. And how do we calculate this atomic size factor? Is by subtracting the atomic radius of the solute minus the solvent, dividing by the solvent and multiplying by 100. If it is less than or equal to 15, the Hume-Rotary rule is applied. The substitutional defect can be done if it's greater than 15. the solubility is limited. So let's read this definition. Extensive substitutional solid solution occurs only if the relative difference between the atomic diameters, radii, of the two species is less than 15%. If the difference is greater than 15%, the solubility is limited. Comparing the atomic radii of solids that form solid solutions, the empirical LUD given by Rotherley is given as this equation right here. So basically, if the difference between the atomic radius is too big, then there's no point on doing the substitutional defect to strengthen the material. The next rule is the crystal structure rule, which is for appreciable solid solubility, the crystal structures of the two elements must be identical, otherwise it won't work. Rule number 3, valency rule. A metal will dissolve a metal of higher valency to a greater extent than one of lower valency. The solute and solvent atoms should typically have the same valence in order to achieve the maximum solubility. This is the most important part of the rule. They must have the same valence. And the last rule is the electronegativity rule, which means that the difference in electronegativity close to zero gives maximum solubility. The more electropositive one element and the more electronegative the other, the greater is the likelihood that they will form an intermetallic compound instead of a substitutional solid solution. The solute and the solvent should lie relatively close in the electrochemical series. That one is pretty straightforward. We can move on. So we can, now that we've been over vacancy and interstitial point defects, there's some names and categories for when both of them happen in a material. The Schottky defect occurs when opposite charged atoms, which also means cation and anion, leave their corresponding lattice sites and create a pair of vacancy defects. So, as you can see, this is a much bigger vacancy defect than the one that we saw previously, and that's because both the cation and anion left. Since both cation and anion leave the lattice sites at the same time, the overall electronegative neutrality of the crystal is maintained. However, density reduces because of the vacancies. Occurs in ionic crystals, where the size of anion is almost the same with the size of the cation. That's very important right here. The next category is Frenkel defect, which is a type of point defect where an atom, better to say an ion, especially cations, leave its original lattice site and occupies an interstitial position on the same crystal. So right here we see the Frenkel defect. And why does it say especially cation? Because they're smaller and they are more able to go from their original lattice sites to the interstitial position, which is not a lot of space for the anion, which is much bigger than the cation, to move. Usually, this type of defect is observed in ionic solids, where the size of anion is substantially larger than the size of cation. And that is a review of point defects. In the next video, we're gonna go over linear and planar defects.